Welcome to the wonderful world of astronomy. This is Chapter 4, Making Sense of the Universe. In this video, we'll look at Part 4, Gravity. Sir Isaac Newton began pondering what makes an apple fall. This was according to one of his biographers about the summer of 1666. Why does an apple, or really anything, fall downward? Why doesn't it ever fall upward or sideways? And as I've mentioned in a previous video, as he was pondering what makes an apple fall, he got to thinking about what makes the moon move across the sky. And even though they are very different motions, the moon does move, we can say, sideways across the sky, and seemingly very slowly, as opposed to an apple falling straight down. He began to realize that it's the same force that's moving them both, and he called it gravity. He published his universal law of gravitation in 1687, and in this video I will describe the universal law of gravitation. It's a very good description mathematically that helps us to describe the motions of the apple falling, or the moon across the sky, or the motions of planets, stars, and galaxies. Now, fundamentally, it is not an accurate description of what gravity is at the core. Albert Einstein came along in 1915 and published a very different description of gravity, but still, the law that Isaac Newton wrote down is still very useful for us today. So let's look at the universal law of gravitation. Look at the picture down below. We have two masses. Now, those could be stars, they could be planets, it could be a pencil and an apple, it could be anything that has mass. And here's what the universal law of gravitation says. First of all, every mass attracts every other mass. So this means we're not just talking about things in space like planets and stars and galaxy. Everything that has mass is attractive to every other thing that has mass. And this is atoms and molecules as well. This is your body. Number two, attraction is directly proportional to the product of their masses. You can see the mathematical formula down below. This says force of gravity equals, and there is, first of all, capital letter G. Now, capital letter G, that represents a constant. You don't need to know what that constant is, but just as in a previous video, I said the speed of light is a very, very large number. You can think of this capital G, it's called the universal gravitational constant, as a very, very small number. It's 6.67 times 10 to the negative 11 power, a very small number. The ramification of it being a small number is that you need, in order for the gravity to be felt, the force of gravity to be felt, the product of the masses, which goes in the numerator here, has to be very, very large to overcome that small constant. So in the numerator, we have the mass of object 1 times the mass of object 2. Now, a minute ago, I said this can involve not just planets and stars, but it could be your body. Think of your body and something as you look around the room, maybe a book or a drink of water, whatever. There is a gravitational attraction between you and that thing. However, it's negligible. It's so close to zero because your masses, the mass of your body and the mass of that object, are not big enough to overcome the very smallness of that universal gravitational constant. So really, gravity is only going to be felt when you're talking about at least one of those objects being something very massive, like a planet or a moon or something even more massive, a star or a galaxy. But in the numerator, the product of the masses. So the more massive those objects are, the more the strength of gravity between them. The force of gravity is also determined by, let's look to the denominator. And remember in math, when you divide by a denominator, the larger the denominator, the smaller the fraction is going to be. So rule number 3 says the attraction is inversely proportional to the square of the distance between their centers. Inversely proportional means distance is down there in the denominator. So as I said a minute ago, the larger the distance, the smaller the force of gravity. And it's not just the distance, but the distance squared, which means when we move these two objects away, the force of gravity falls off very quickly. Now, we will talk in a bit about your weight. Remember that your weight is the force of gravity, Earth pulling down on you. And it's determined by this. It is the gravitational constant times the mass of the Earth times your mass divided by your distance squared. And then you have to think distance squared from what exactly? From the Earth? Well, if you're standing on the ground, you're practically no distance, but it's really from the center of the Earth. You've seen this slide before in a previous video. If you weighed 100 pounds on Earth, you would weigh these different amounts on these different planets or moons. And that has to do with, as I was showing on the last slide, it has to do with the mass of the planet itself divided by your distance from its center. So it's not just enough to think a big planet or a small planet. It has to do, first of all, with its mass, such as Jupiter is a very massive planet. It's 318 times the mass of Earth. But that doesn't mean you are 318 times heavier on Jupiter. So while it is 318 times more massive, the force of gravity is diminished by the fact that Jupiter is also a very large planet. So you're much farther away from the center of Jupiter than you are from the center of the Earth when you're standing on the Earth. So the force of gravity gets diminished. And in the end, the fact that it's more massive kind of wins out. And so you weigh 2.36 times more what you do on Earth. The moon is low mass. It's also low radius. And so it's a smaller planet, we can say, but we actually have to do the calculation. So low mass means less gravity, but low radius, because you're closer to the center of the moon if you're standing on the moon than you would be to the center of Earth if you're standing on Earth. That would go to increase the gravity because that's smaller distance, but in the end, the smaller mass wins out, and effectively you have less gravity on the moon. Now, in terms of sending spacecraft beyond Earth or beyond any planet, gravity determines the escape speed, how fast you have to be going to escape from Earth's gravity. If you want to go to the moon or send a spacecraft to another planet, you have to escape from Earth's gravity. Now, you can imagine if you take a ball and throw it straight up in the air, just with a little bit of speed, it doesn't go very high. You take the ball, you throw it faster, straight up into the air, it will go higher. And if you take it and you throw it as fast as you can, it will go even higher, but it eventually comes back down. Well, escape speed is the speed that if you throw it up at that speed, it will never come back down. It will escape from Earth's gravity. And so for Earth, the escape speed is 11.2 kilometers per second. That's probably about 7 miles per second, something like that. We're not going to be plugging numbers into this equation, but I just want you to see it's a pretty simple we do this in my physics class, derivation. This is that the kinetic energy is equal to the potential energy. Those are concepts you've learned about in a previous video. In the end, the escape speed from a planet, a star, a black hole, whatever, is the square root of 2 times, there's that universal constant, which doesn't change throughout the universe, the mass of the thing you're trying to get away from. So that makes sense. The more mass it is, that means there's going to be stronger gravity. You're going to need to go faster away from it, divided by your distance from it. Now, that doesn't necessarily mean the radius of the planet. Sure, that is the escape speed if you're, look at my red marker here, if you're at the surface, then that is your distance from the center. But let's say you're already in orbit. Let's say you're right here in orbit around the Earth and you have a spacecraft, and from that position you want to escape away. Well, gravity is weaker up there because you're already farther away than the surface. And so it's not going to take as much escape speed. So here, if you look at my red marker, if you want to escape from this distance and you want to know what is the escape speed from here, well, it'll be, according to the formula at the bottom, square root of 2 times g times the mass of the Earth divided by whatever your distance currently is from the center of the Earth. Next, how does Newton's law of gravity extend Kepler's laws? Remember Kepler's 3 laws of planetary motion. We talked about that in chapter 3. Kepler's laws apply to all orbiting objects, not just planets. So remember Kepler's laws, he said that all planets orbit around the sun in an ellipse. Their orbits sweep out equal areas and equal times, and the period squared is equal to the semi-major axis cubed. And as I told you back in chapter 3, Kepler did not know why those things were true. He just showed that they are true. And that was between 1610 and 1618 that he published those 3 laws. And then it was several decades later that Isaac Newton, when he formulated his law of gravity, he was able to show the theory behind Kepler's laws. And first of all, he showed why they are true, but also he showed simply that they are true. So Kepler's laws that he came out with in the early 1600s and Newton's laws that he came up with in the late 1600s all are, they have good practical application and are seen as fairly true even today, many centuries later. So Isaac Newton said it doesn't just apply to planets, it applies to anything that's in orbit around the sun. And later on, after Newton's time, then we figured out, or any other stars, not just our sun. Isaac Newton showed that ellipses are not the only possible orbital paths. Orbits can be bound. So a bound orbit is an ellipse or a circle. I group those into the same category. So here's an ellipse. Bound means it is gravitationally bound to the sun, or the star that it's going around. A circle is just simply an ellipse that has 0 eccentricity. It could be unbound, so a parabola, you can imagine a comet coming in and then swooping off, or an unbound hyperbolic orbit. This is a hyperbola, comes in, looks a lot like a parabola. They're mathematically just a little bit different. So unbound means it is gravitationally pulled in, but then it goes off into outer space and it's gone. So it's not in a bound orbit. By the way, you can also have a bound parabola. I didn't mention it on this slide, but just throws something up in the air a little bit to the side and it comes back down and it makes a parabola. So those are the possible shapes. Now those shapes are called conic sections because, as Isaac Newton described, all those shapes geometrically can be found by taking a cone and slicing it in different directions. So an ellipse you get if you take a cone and you slice it at an angle that doesn't intersect the base, and so there's an ellipse. Although if it's perfectly parallel to the base, you get a circle. Now, if you take it and slice the cone in such a way that it intersects the base at a 90-degree angle, you get a hyperbola. And slice it so it intersects the base at a non-90-degree angle, you get a parabola. So Isaac Newton, I think it's very neat to see that he showed in the late 1600s that all possible orbits of spacecraft, of planets, of comets, all these things, they are shown geometrically and mathematically. They are described by the sections that you get when slicing a cone. And again, those are called conic sections. So far in this class, you've sometimes heard me talk about planets in orbit around the sun, that they go around the sun in ellipse. That's what Kepler said. And if we want to get more precise, it's not exactly true, so I want to expand on that a little bit. It's for purposes of planets going around the sun, it's mostly practically true, but let's get more into it. When you have two orbits, or I'm sorry, when you have two objects that are in orbit. It's not that one object orbits around the other, but rather the two of them are in a mutual orbit around their center of mass. So look at the picture at the top. Let's not think about for the moment a star and a planet, but let's think about two stars that are in orbit around each other. So the first question could be, which one orbits around the other one? Which one is the dominant star? And if they have equal mass, neither of them is dominant. But you could say that the one with the more mass has more dominance in proportion to the ratio of their masses. So let's take these two stars of equal masses. The center of mass lies halfway between them, and they will orbit around that center of mass. So star 1 might go around a circle in that way. Star 2 will go around a circle that way. They will dance around that common center of mass. Neither one is orbiting around the other, but they orbit around their center of mass. Now, let's make star 1 on the left be a bit more massive. Let's make it twice the mass of star 2. Their center of mass, think of that as the balancing point, where if you could stick your finger under this, where it would balance on your finger. The center of mass lies closer to the more massive one, so they will go around that center of mass. Star 1, the more massive one, will make a tighter circle going around like that, and star 2 will make a larger circle going around like that, but they will always have this point at their center. Now let's consider a star and a planet. Now, this star, we'll call it mass M, and the planet has mass 1/100th of that mass. Now, really, as planets go, that would be a very, very massive planet. Jupiter, which is the most massive planet in our solar system, is only 1,000th the mass of the sun. But let's just go with what the chart says here. The star is so much more massive than the planet that the center of mass actually lies inside the star. And so while we can very approximately say the planet goes around the star, it and the star are actually in orbit around their center of mass, which is right there. So the planet will go in a nice wide ellipse or circle, and the star is actually going to wobble as its center moves around that center of mass. And we see that in stars when we look out at other star systems. We see stars that have a little bit of wobble to them. And that's actually a major way that we discover planets around other stars. They're called exoplanets. Very often, most often, we don't actually see the planet. What we do see is the wobble that the planet gives the star as they both orbit around their common center of mass. And so, for example, this is a simulation of two stars where the blue one is 3.6 times the mass of the orange one, and the center of mass is the green dot in the center. So this is what their orbits would look like. Newton's laws of gravity and motion showed that the relationship between the orbital period and average orbital distance of a system tells us the total mass of the system. All right, now think of that paragraph that I just read as it applies to Kepler's third law of motion. Kepler's third law of planetary motion says that the period squared, the orbital period squared, is equal to the semi-major axis cubed. So that's orbital period and average orbital distance. But now Newton came along and said there's much more to it than that. The relationship between the period and the orbital distance can actually tell us the mass of the system. Now, the system in this case would be the star and the planet, or the two stars. Now, Kepler wasn't thinking about two stars in orbit around each other. He was only describing the orbit of a planet around the sun, but this can be expanded more. So, for example, Earth's orbital period of 1 year and its average distance, 1 astronomical unit, can actually tell us the sun's mass. The orbital period and distance of a satellite moving around Earth tells us Earth's mass. The orbital period and distance of a moon of Jupiter tells us Jupiter's mass. This is Isaac Newton's version of Kepler's third law. Now, if you look at the equation on the left, Remember Kepler's third law. I told you that p squared, that's the orbital period squared, equals a cubed, semi-major axis cubed. And when Kepler wrote that, p squared equals, let's jump over here, a cubed. That was specifically talking about planets going around the sun. But Isaac Newton came in and filled in all of this in here. And so what it involves is the strength of gravity, remember that universal gravitational constant, m1 and m2. That's the sum of the two masses. So maybe we're talking about a planet going around the sun. Maybe we're talking about two stars in orbit around each other. It doesn't matter. If we're talking about any two objects in orbit around each other, this is the relationship between the period, the semi-major axis, and now Newton added in the sum of the masses. Algebraically, we can solve this equation and get the sum of the masses equals all this that's on the right. And all this that's on the right is the semi-major axis cubed, the period squared, universal gravitational constant, and some other constants, 4 pi squared. What this means is that today we can look at when we see two objects, maybe two stars, two black holes, neutron stars, whatever they are, if we can measure their period and we can measure how far away they are from each other on average, we can plug those into this equation and get their masses. So this is a good way to determine the masses of stars. So what have we learned? What determines the strength of gravity? Gravity is directly proportional to the product of the masses, and so that's the mass of the first times the mass of the second. It's inversely proportional to the square of the separation distance. How does Newton's law of gravity allow us to extend Kepler's laws? First, it applies to other objects, not just planets going around the sun. Newton's law of gravity applies to any objects that have mass. It includes unbound orbit shapes, such as a parabola or a hyperbola. And it can be used to measure the mass of orbiting systems, such as stars that are in orbit around each other, or planets that are going around other stars, or moons going around planets. As we wrap up chapter 4, I want to talk about orbits, tides, and the acceleration of gravity. Here you see a picture at a beach of low tide on the left and high tide on the right. And if you've spent significant time at the beach, you know that that's a regular occurrence every day. In fact, there are 2 high tides and 2 low tides. It's in a cycle of 6 hours and 50 minutes. So about 4 tides, either low tide or high tide in a day. Before we talk about tides, let's talk about orbits and changing an orbit. What can make an object gain or lose orbital energy? Remember that energy is conserved, and so that means that you can't just create or destroy energy, but it can be transferred to other objects. It can be transformed. And so let's take a comet that's coming in on this path, an unbound path around Jupiter. The orange circle represents Jupiter's orbit around the sun. So the comet comes in, and a gravitational encounter, such as with the planet Jupiter, can take energy from the comet. And so while the comet comes in, it's got this nice unbound orbit around the sun. Jupiter can take away its energy gravitationally and put the comet in a bound orbit around the sun. So now we have that elliptical orbit. Another thing that can cause an object to lose gravity could be friction or atmospheric drag. And so, for example, when we have the International Space Station orbiting around the Earth, we say it's above the atmosphere, but it does encounter some little bits of Earth's atmosphere, a very low density. And so there is a bit of atmospheric drag, which serves to degrade the International Space Station's orbit. So they have to do course corrections every now and then to fire little rocket thrusters to keep it in its steady elliptical orbit. How does gravity cause tides? Remember that According to Newton's law of gravitation, the farther away something is, the farther away two objects are, the less gravity is. And the closer they are, the more the gravity is. And so let's think about the Earth, which is covered with water. All the oceans are connected to each other. And think about the moon's gravitational attraction on the Earth, and the distance would be the distance from the moon to the center of the Earth, and compare that with the gravitational attraction between the moon and the water on the near side of the Earth. Well, because the water on the near side is closer to the moon than the center of the Earth, there's more gravitational pull. So the moon's gravity pulls harder on the near side of the Earth than on the far side, and it lifts that water up. So people who are right here where the moon is overhead are going to experience high tide. Now let's think about the other side of the Earth. There's water on the other side, and it is not being pulled on as hard as the center of the Earth by the moon. So the moon is effectively lifting the center of the Earth, lifting the planet Earth away from the water that's on the far side. Well, if you're standing on that far side, where my pointer is, you will experience high tide. Even though I just said that the Earth is being lifted away from that water, what you'll experience is that the water seems to be lifted up. So as it says in the caption, the gravitational attraction to the moon is weaker here, weakest here, and strongest here. The difference in gravitational attraction tries to pull Earth apart, raising tidal bulges both toward and away from the moon. So they get high tide if the moon is directly overhead or if the moon is directly underfoot. Now, where is all this water coming from that's making high tide? Well, remember, all of the Earth's water, all the oceans, they're all connected in one system. And so that water is actually being drained from here at the top of the picture and here at the bottom. So if there's a 90-degree angle between where you're standing, such as where my marker is, and where the moon is, you'll be experiencing low tide. So as the Earth rotates, let's follow my red marker. Let's imagine someone standing right here. That person is experiencing high tide, and the Earth rotates. About 6 hours later, this person will be at low tide. The Earth keeps rotating. The person's at high tide. Earth keeps rotating. About another 6 hours later, low tide. And then another 6 hours later, back at high tide again. Now, earlier in this video, I said it is not a 6-hour cycle, but rather a 6-hour and 50-minute cycle, a bit more. And the reason is, in order to get high tide, the moon has to be directly overhead. But remember that in the day that it took for the Earth to rotate around, the moon is no longer sitting here. The moon has moved about 1/27th of its orbit. So now the moon is where my red marker is. And that means that to rotate back to high tide again, you have to be right here. You have to have caught up with the moon. And so I misspoke a bit ago earlier on this slide. I said it's 6 hours and 50 minutes. That's incorrect. It's about 6 hours and about 16 minutes. The full cycle is 24 hours and 50 minutes. So between high tide and low tide should be about 6 hours and 16 minutes, so that the entire cycle is about 24 hours and 50 minutes. That is the end of Chapter 4, Part 4, Gravity, and that's also the end of the Chapter 4 videos. In Chapter 5, we will look at matter, what makes up matter, and we'll look at the third type of energy called radiative energy, which is light, and we'll look at the interactions between matter and light. That'll be Chapter 5. Have a great day.